Imitation is the sincerest form of flattery. The term biomimicry was first coined in the late 90s by biologist and author Janine Benyus. In her book, Benyus outlined how studying and emulating nature's time-tested patterns and strategies could lead to sustainable and innovative solutions in various fields, including engineering, architecture, and materials science. However, the practice of looking to nature for inspiration dates back much further, with historical examples such as Leonardo da Vinci's studies of birds to design flying machines. One might argue that learning by observation is a hallmark of the human species. Nature has had a lot of time to experiment and get it right. And so in the pursuit of technological innovation, we can leverage this eons-long trial and error to our advantage. Why try to fix something that isn't broken? And we see it all around us in just the last few decades. On land, underground termite tunnels provide natural ventilation systems that inspire energy-efficient HVAC design, while the desert beetle's textured exoskeleton inspires novel water harvesting technologies. In the air, the peregrine falcon's wing design inspires better maneuverability for high-speed aircraft, while the kingfisher's beak inspired the Japanese Shinkansen bullet train to reduce aerodynamic drag and noise. And at sea, the jellyfish's efficient anatomy inspires more effective underwater propulsion, while the octopus is a master of camouflage and adaptability. The octopus alone is responsible for multiple breakthroughs in technology and innovation. Consider data centers. These sprawling facilities filled with rows of servers are the backbone of our digital age, powering everything from streaming services to edge computing. Could we take these natural inspirations and apply them to the very heart of our modern digital infrastructure, especially in the age of AI? While the focus on AI has primarily been on the processing innovations from big names like NVIDIA, there's also a natural evolution happening within other systems of the data center, influenced by the eight-armed wonder found beneath the waves. It involves a unique blend of the latest technology nodes and legacy devices like the humble microcontroller. How can Microchip technology bring the next evolution of AI from the edge to data center? Let's go beyond the Microchip and hear a story of empowering innovation to enhance the human experience. Our guest today is Brian McCarson. Brian is Corporate Vice President leading the Data Center Solutions Group here at Microchip Technology. He joins us today from our corporate headquarters in Chandler, Arizona. Welcome, Brian. Thank you for joining us on Beyond the Microchip.
Thank you for having me. Excited to be here.
In the intro, we briefly talked about biomimicry as a science and how it can influence technological innovation for humans. But you make a further connection on systems designed from the edge to the data center. What can you tell us about that?
Yeah, well, it's really interesting that when you were giving your introduction, you were talking about one thing that makes humans unique is our ability to observe the world around us and try to understand why things work.
Mm-hmm.
How does one organism swim so efficiently? One have the ability to fly? And I think throughout time, we've looked around us to understand how the world works and use that to study opportunities for cause and effect relationships. And whether it's discovering pharmaceutical compounds from chemicals in the Amazon rainforest and using those to try to improve patient outcomes, we've been studying the natural world in other ways like the ones you mentioned. And what I find fascinating is throughout my career, when I encounter a barrier that hasn't been overcome, I've always been really intrigued to look at the world around me and see, are there other places where this has been solved?
Mm-hmm.
And engineers do this regularly. You've seen innovations in automotive spill over into industrial manufacturing and vice versa. Innovations in consumer electronics, like what NVIDIA famously did with the GPU to make gaming experiences better, spill over in artificial intelligence and eventually transform that entire company into a completely different business than what it was before. There can be beauty in the adjacencies of how technologies can solve certain things, but there's also natural systems that exist in the planet that are quite fascinating to me. And when I think about this new era that we're in, where the world is connected, we have sensors connected to devices, devices connected to other devices, connected to networks, connected to the cloud. You've got this whole revolution of artificial intelligence that's been exploding from an innovation perspective, with these massive investments in data centers that are creating these enormous models that take, hundreds of thousands of person years of innovation to create a massive model. But how is this all going to come together in a way that's going to be an efficient way to manage? And when you talk about edge computing in particular, and the role of the data center and what's happening at the edge, there's something that to me is really fascinating about that system architecture, if you will. If you think about the blueprint for how technology works, like
Right.
your smartphone connects to a central app if you're going to go get a Lyft or an Uber or something, right? The device guides you. It's computing at the edge. It's connecting you into a bigger network, but it has to work in harmony with the cloud. And if you think about how humans used to measure intelligence, early evolutionary biologists would measure the weight and volume of brains to try to determine how intelligent a system was. And when you think about architectural design for technological innovations, it's not always just about central intelligence that really makes for a good experience. I think we would all be pretty frustrated if we didn't have apps on our phone that could help drive things. So it's the combination of having a central architecture, the central brain, and all this power at our fingertips at the edge that really creates something unique. And there's this field of biomimicry. Something that's been fascinating to me is when scientists started really studying this really strange looking creature that looks like it's out of a science fiction movie, an octopus.
Mm-hmm. Aliens here on Earth.
Aliens here on Earth. You look at these creatures and you see their behaviors and you're like, how on earth does it do that? How does it change the texture and color of its skin in a millisecond to adapt to its surroundings, to camouflage itself, and then just pop right back and then go about its business? And there's an interesting lesson that I've learned over my journey between, balancing the cloud and the edge in artificial intelligence solutions, which is this magical mimicry of the octopus's neurologic architecture.
Mm-hmm.
What's fascinating, if you just try to do by brain mass, the octopus wouldn't show up as necessarily that smart. It's got a big brain for its body volume, but like the way we like to compare, this is why Homo sapiens are so smart. Look at how big our brains are compared to
Right.
everything else. But most of an octopus's neurons are outside of its brain. You think, well, why would it have most of its gray matter outside the brain? Well, that has been a necessity in its evolutionary pattern. An octopus doesn't have, sharp fangs or claws or spikes or anything to defend itself. Its defense mechanism is its intelligence and its adaptability. And that's also its predatory skills. So it survives and thrives in its environment because of its distributed intelligence. And so what does that mean? Well, it means that on the skin of an octopus's surface that has neurons, and those neurons also connect into photoreceptors. So the same sort of photoreceptors that exist in the back of your eye that detect different colors of light in the visible spectrum, those sort of cells in more crude form or elegant form, depending on if you're looking for simplicity of function, those cells can detect the colors of its surroundings in the skin. The skin can actually see its surroundings, and there's all these independent muscles that exist inside the skin, which can flex and relax to change the pigment of the skin. So you
Without thinking, completely instinctual.
Yeah, it does it all at the skin level. It doesn't need to go connect back to central brain to figure that out. It doesn't have to go back to its data center.
Right.
It can do it all at the edge. It can do it in the smartphone at the skin, essentially. And so it can manipulate its body appearance to seamlessly match the surroundings that it's in. And I remember even observing an octopus in the wild once and watching it swim across a very colorful coral reef with lots of different texture. and watch it change its camouflage while it was swimming, because it saw me watching it and wasn't sure if I was a predator or just something interesting.
And each individual tentacle has that camouflage capability?
Yeah, and so as it's swimming, you're just watching it like recreate its entire appearance as it swims over objects that don't look like how it looked, and it adapts itself. And all of that computational power exists at the edge of its nervous system, at the skin level. Now, humans have neurons too outside our brain. I think most people are aware that you've got gray matter in your fingertips. This can be really helpful if you touch something hot. You don't sit there and have your eyes watch your hand melt when you touch a hot pan, and then your brain decides, oh, I should move my arm. Before you even say ouch, your hand is already reflexed away. Because the neurons in your skin are empowered to give signals to the muscle tissue around it to move. And this system architecture is actually a smart way of balancing central computing versus edge computing, and it works well in biological systems. So when I think about data center architectures, when I think about solution architectures in businesses and what makes humans have better patient care experiences in the medical field, well, wouldn't it be great if the physician at your local urgent care had access at their fingertips to a compendium of information, and they could scan your body really quick and look for things that could be going wrong, and use all that central intelligence right there at the edge to give you a better diagnosis and have better patient outcomes. I can see at both the solution level and at the digital level having a distributed architecture from edge to cloud being a good choice. And I think the octopus is a really interesting example of that.
So when we talk about edge computing for the layman, the cloud, I think people have kind of wrapped their heads around and they kind of understand is that it's a server or it's a computation source that's away from them. And we like to joke that it's up in the cloud. It's not really up in another cloud. It's distributed amongst other computers. But the idea is when you put through a command, either through your phone or through your computer, it's going to go ping that server system or that data center, and it's going to feed back a result. But edge computing is more than that. It's not just a passive terminal accessing the cloud. There's actually some computation being done at the level where the human is, right?
Exactly.
Would that be a good way to think about it?
That's a great way to think about it. Most of us are, we take for granted the fact that we have, in your smartphone, in your pocket, your camera can do AI inferencing. That's when you do your face detection setup. You're basically training a local model right on your phone to be able to recognize your face, and that's your biomarker that gives you an extra layer of security. It doesn't even have to store that information in the cloud. It can store it right locally on your phone. But the infrastructure for that, this is a large model that was developed in the cloud, and then you just push the necessary data to everybody's phones, and then people can have that access. So I like to think of that edge computing as the kind of things that you expect to happen on your mobile device is a really good example compared to what happens in the cloud. Certainly when you're ordering a lift, you're interacting with your edge device, you're seeing how close is the vehicle, you're choosing to leave a tip and a rating and things. All that information gets sent back to the centralized cloud, but you're not having to directly interface with the cloud to do all the actions, just the ones that are really necessary for your experience. And to me, that's where the balance comes in. The best system architectures and some of the most successful solutions that I've seen actually scale in the market and deliver better outcomes are the ones that strike the balance between where does computation need to happen at the edge, where does it need to happen in the cloud. And from a biomimicry perspective, you think about the octopus. Well, if the octopus's central brain was having to look at all of its 8 tentacles and decide, okay, tentacle number 7, sorry, you're not cutting it. I need you to step up your game here.
Active management of limbs.
Active management of limbs. You're not camouflaging to the same degree. Tentacle 8, you're the overachiever again. Keep it up. No, the central brain can be using its eyes to be scanning the horizon for predators, to be scanning for prey, for a mate, trying to figure out whatever an octopus philosophizes about. I think they're pretty intelligent creatures, so maybe they're wondering where they came from or something.
Planning our domination.
Planning world domination. But that's a similar example of where the centralized brain can be using higher level functions and then delegate some of those tasks to other in a sense, agents that are running on behalf of the central system at the edge. And one thing that to me is fascinating is, if there's anyone on the planet that should be considered credible in the field of AI, it should be Jensen, the CEO of NVIDIA.
Mm-hmm.
Jensen has been openly talking about in 2025 at CES and GTC that as exciting as this ChatGPT generative AI movement has been, that really isn't that's maybe where the puck is today, but that's not where the puck is going, to use that hockey analogy.
Mm-hmm.
The world is moving towards agentic AI. And the way I think about agentic AI is these are the agents that reside at the edge that are going to be doing these tasks for us that are delegated out. It's the photoreceptors and muscles that help an octopus camouflage are agents that are working on behalf of that octopus, and the central brain is the conductor of the orchestra. And I think when you think about system architectures, using that same sort of philosophy works great in a lot of solutions. You can think
about that distributed intelligence model.
That's right, yeah. So the data center can be where you train your large model on an aggregate data set and come up with a great way to have some breakthrough in productivity or patient diagnostics or better retail outcomes or better industrial machinery operation, autonomous driving, whatever that use case is. But then you want to go deploy that to all the vehicles in the fleet, to all the robots in the factory, to all the retail stores that are gonna be essentially agents working on behalf of the larger organism in that system. And so as I've been thinking about the right architecture for the future, I've been dissatisfied over the past few years with the obsession of cloud computing and all AI occurs in the data center and that's where everything happens. Because in my mind, I kind of know that there's got to be that balance between the edge and the cloud. So for those who don't know, I just recently joined Microchip, having had a multi-decade career in artificial intelligence. And one of the things that got me really excited about coming here is just knowing that balance between centralized intelligence in a data center and the need for those agents that exist everywhere on the planet. Thinking about the broad reach that Microchip has all across the planet in its embedded control systems and some of the field programmable devices, ASICs, microcontrollers, and some of the ridiculously advanced technologies that Microchip brings into the data center world. I thought, wow, what an absolutely perfect place to go be a part of a team making agentic AI a reality.
Yeah, so we don't have, well, there are some processing solutions within our lineup, but we're not really known for the central brain as much as we are, what would you say, the nervous system or the outlining components? What was your analogy going with that?
Yeah. So the way I think about it is I almost let's use the human's nervous system as an example. And let's say we've got two hemispheres in our brain. You got your right brain and your left brain. We'll call one the data center GPU and one the data center CPU. Mm-hmm. Then you've got this spinal cord nervous system. That's your wide area network infrastructure. Mm-hmm. That's getting you from the data center to your 5G network or the Wi-Fi hotspot that you're connecting into. And then the edge devices are all the muscles, the nervous systems, the fingers, the hands, the eyes, the sensory organs that are what we interact with as humans in our body. So that's the edge computing portion of it. And Microchip traditionally plays at that edge space. We help sense the world around us and bring intelligence and the control to everything from an intelligent coffee maker, an appliance, all the way to autonomous driving. And
we're very good at moving things from point A to point B and back.
Absolutely, yeah. But maybe not the computational horsepower thought leader. Mm-hmm. And so we'll say those two hemispheres of the brain are the NVIDIA GPU and the AMD Intel CPU or whatever working in unison to try to have the most advanced thought and the most advanced computing. But Microchip's data center products are like the connective tissue. I think the corpus callosum is what we call that fabric that connects one side to another. And when you've got a microchip enabled data center, the switch technologies that we have, the memory controllers, the storage controllers, are the ones that are getting those packets of information from the CPU to the GPU, from the memory, from the solid state drive, and we provide all that connective infrastructure, then all the way through the network, all the way to the edge. So that's really where I see microchip as that central nervous system with which the brain can operate on,
which you can't live without.
Which you can't live without. Yeah.
So where you were referring to really some of the bleeding technologies that we have within our portfolio, and I don't know that microchip traditionally is associated with the bleeding edge or the advanced technology nodes. What were some of those areas that you've discovered in your short time here?
Well, yeah. So you think about so much discussion around the semiconductor foundry ecosystem, and NVIDIA is building these incredibly powerful, well-designed GPUs. They're using TSMC as their foundry.
Mm-hmm.
Most people know NVIDIA doesn't have factories. They outsource that to the foundry ecosystem. And they're running on TSMC's latest tech nodes. The 3 nanometer node, for example, is in production. And what most people don't realize is all that data center infrastructure that we were referring to, that corpus callosum, the medulla oblongata, the spinal cord, all that connective fabric is built on microchip. So we also run in the 3 nanometer node, and so we're running side by side with the likes of NVIDIA, and Apple, and Intel, and AMD, right there in the latest generation technology nodes, so that we can have devices that can switch at speeds that don't make the GPU or the CPU the constraint.
Mm-hmm.
So we've got to get packets from point A to point B and back again as efficiently as possible. So, that's creating, the latest generation switch can have 800 million gates, 144 plus lanes. You're talking about 8 plus terabit per second data transfer rates. When you look at the aggregate system, I mean, ridiculously large amounts of data going through these data centers. And so being able to provide that central nervous system infrastructure to let those GPUs and CPUs run really well is exactly what we do. And that's pretty fascinating to me. But then having an efficient way of connecting an entire network of edge systems that are not going to be in the data center. Or maybe you have an on-prem data center in a smart factory or something right there, and it's coordinating all the robotic systems and everything else, the smart machinery. But being able to be that whole connective tissue all the way from that builds the whole organism around that data center is really exciting.
As we're thinking about the octopus and we're thinking about that distributed intelligence you were talking about, you think that there's actually, and I'm going to paraphrase you here, but you think there's actually kind of little brains at the end of the tentacle, right?
Mm-hmm.
Is there a connection there to data system architecture?
Certainly, yeah. So when I think about that system architecture all the way from the edge to the cloud, whether the edge is the vehicle, the smartphone, smart appliance, whatever that is, the smart camera, that's really the edge. And having some intelligence there makes a lot of sense. It's really expensive to stream data from a smart camera all the way through the network, all the way to the cloud, just to have an expensive GPU say, oh yeah, that's someone I just detected. Okay, now send that signal all the way back through the network again. Now tell the camera, okay, yep, you saw something. Go ahead and send an alert to your owner. That just doesn't make sense. And so having the right amount of compute at the edge to do the right task, to me is an economic decision, and it's a business outcome decision. It's a human experiences decision at how much compute you should have at the edge. I think Apple has done a phenomenal job of understanding the consumer of a smartphone user and trying to balance what's the best experience I can deliver in someone's hand, and how much compute do I need to have in order for them to have a great experience
without taxing the central brain.
Without taxing the central brain unnecessarily, because then it's slower. You think about innovations with Google Maps. It was very similar. It's how do I pre-cache information based on my actual location, so I can very quickly have a good experience and not sit there and watch the little bars spin around in a circle waiting for me to get access to data.
Yeah.
So balancing that edge computing capability really delivers a fantastic experience. And if you think about the impatience of humans, I think about
latency is a 4-letter word.
Latency is terrible. If it takes me a second to interact with a feed on Instagram, I feel like, what's wrong? I lose my connection? What's going on here? Something's broken. So we've become quite impatient with the delay that we can have in having a technological experience. But even at the speed of light, it can take time to be able to get information from that edge device all the way through the network to the cloud, have the cloud compute it, and then send it back. Not unlike what the octopus deals with. And when you think about latency, that's where the octopus's system architecture really comes to life, because an octopus has so many predators, and it's trying to eat at the same time and be a predator. But the things are pretty tasty to other fish and apparently a lot of humans too. So as it's hunting around in a coral reef, it's inserting its 8 tentacles into all these crevices without the ability to have its 2 eyes look at where it's going.
Wondering what it might find.
And it needs to be able to recoil if it finds something it didn't want, like a moray eel or something. It needs to be able to latch on with its little suction cup mechanisms autonomously and then bring it up to its eyes, to its face, sniff it, taste it, sense what it is. And it can do that with all 8 tentacles independently. But when you think about hunting and protectionism, I don't want to get eaten by an eel. I want to find my next meal at the same time. That's where latency is really important. And so, having a central brain with 2 eyes trying to monitor
scanning
in dark
the horizon
places,
for sharks,
and trying to figure out where every tentacle's going while it's on the hunt is just ridiculous. You couldn't do that.
Yeah.
And it wouldn't make evolutionary sense to put, sensitive eyeballs at the end of every one of its tentacles. So it's really designed itself in an evolutionary efficient way to be able to hunt well from a latency perspective. And so that's another thing that I've always found fascinating about the octopus's system architecture is there's a lot of different areas where we can learn from. Latency is one, autonomy is another, offloading of tasks is another. There's a lot of different potential benefits from an architecture like that. And so, when I'm talking to customers about what problems are you trying to solve in your business, what is it that is holding your company back? We get into some of these system architecture discussions and start to talk about what future generations of technology are going to look like. And I often don't bring up the octopus thing because it takes too long to explain. But instead, I just talk about positioning resources where the customer.
What can you delegate to certain areas, right?
Exactly. But in the back of my mind, I'm thinking of a cute little octopus swimming in a nice coral reef somewhere.
Much to learn. All right, so suppose one of our listeners has a use case for this technology. They go, all right, I get it. I understand the edge. I understand distributed intelligence. I can see the octopus. I get it. Where could we send them? Where do you think a good location would be?
Well, yeah, if you, Data Center Solutions is the name of the business I have the honor of leading within Microchip. And that's a great starting point. But what I think a lot of people have found is when they think about their end-to-end challenges, thinking of the Data Center Solutions team as from a system architecture level, we actually solve problems at the edge too. A lot of our customers aren't actually putting their products in data centers. They're putting them in distributed ways for their unique use cases. Some of those out at the edge. They could be in an edge server. They could be in local area network infrastructure. They could be in very complex systems. Any location where you're constrained by traffic, you've got all sorts of different sensors and inputs coming in at the same time, and you're trying to direct traffic from storage to memory to compute devices. That's where world-class switching technologies can help. Anytime you've got a situation where you're constrained by access to memory, that's where a memory controller can help.
Mm-hmm.
If you're struggling from a storage retrieval perspective, that's where a storage controller can help. And so we specialize in these things. Or if you're going over long distances and you need good signal integrity, so that's a place where you can go.
We'll throw a link in the show notes for this episode. We get to one of the best parts of our conversation, Brian, which is the prediction section. So do we have any predictions for the future of data center systems architecture and how that technology could enhance the human experience, like the examples we talked about today? So far, we've got distributed intelligence, which I love. We've got agentic AI. We've talked about latency, and we've talked about a few other topics here. But what happens tomorrow?
To me, the future looks a bit like how Jensen describes it is, yeah, we're going to keep training big models, but the purpose of training the big models is so that you can deploy agents to actually solve real problems at the person level, at the machine level. And so having more of these DeepSeek type moments where if someone announces an amazing breakthrough that changes the field of AI forever, we will probably have dozens of ChatGPT-like moments over the next decade. But they'll quickly be followed on by, and someone else just did the same thing or similar cheaper, and someone else found a way to do it faster. That's what's amazing about human innovation. So I anticipate lots more of that. The oh yes, you did that, well, look what I can do. And that I think is really healthy because that in a sense democratizes the technology to the point that anyone can have access to artificial intelligence. And that's not unlike exactly what Microchip over its history enabled for humankind is making the microcontroller so cost effective, you can put it in just about anything. And as a result, the microcontrollers everywhere. Having agentic AI solutions that become so cost effective, you can put them everywhere without, and base that on a large model that someone did invest a lot of money to go build, to me is where I think the world is going. But there's another element of that, which is a key step along the way. And this is this concept of fine-tuning or retrieval augmentation. RAG models, retrieval augmented generative AI models. To me, the way I think about that is, from a more of how I like to describe it in my brain is, okay, so I built this amazing language model in ChatGPT, but I just want to go create something that's a specific task. I just want to be able to do good resume writing. Do I really need to have access to the full library LLM, and capabilities of the entire LLM, or do I just need a subset of that and then apply it gracefully to a specific use case? That could be a more elegant way of partitioning some of that larger model for an agentic use case. But then what happens if something new occurs? For example, if I think about doing an image search and I want to go create a new AI generated image, but I just saw Kendrick Lamar play in the Super Bowl, and now I want to overlay that on top of it. Do I have to go train an entire new model to
start
do
over
that?
from
Or
scratch?
Can I just do a retrieval augmentation? Can I say, take that model that we spent a year developing or 2 years developing and refining and augment it with a couple of new images and then rerun it, see what I get? Or can I upload my own image and have that be the augmentation? So that idea of little sub models that can derive out of a greater, larger work is really an important breakthrough that still has to be uncovered. We have just started the retrieval augmentation journey as scientists and engineers. And so there's a lot of work that needs to happen. But I think that's going to be where we spend a lot of time, is augmenting models with new information, refining subsets of models to be able to create scalable solutions at the agent level, and then continuing to ratchet innovations, continuing one click at a time to keep turning that ratchet and getting better and better and better as a
Continuing
society.
to outstretch our tentacles.
That's right. Yeah.
Brian McCarson is Vice President of Data Center Solutions Group at Microchip Technology. He joins us today from our corporate headquarters in Chandler, Arizona. Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.